Okay, so in the last video we talked about how to find the components of vectors, and so now we're going to get back to physics and talk about projectile motion. Projectile motion can be one of the more difficult parts of mechanics because basically it involves combining everything we've done so far into one type of problem. Okay, and so we've learned about concepts like, motion with constant velocity, motion with constant acceleration, both horizontal acceleration and vertical acceleration with freefall problems. And we've also learned about how to find components of vectors. Okay, so projectile motion is basically the motion of a falling object in two dimensions rather than one dimension. And so what I mean by that is, for example, if you just drop a ball off of a cliff and it falls straight down, that is a one-dimensional problem because it's only going down. If you throw a ball off of a cliff, okay, then the problem basically becomes from going straight down like this, it turns into more like more like this, where not only is it falling down, but it's also moving off to the side. Okay, so this would be like a one-dimensional problem, and then this would be like a two-dimensional problem. So it has both a horizontal and a vertical aspect. The horizontal aspect is the motion of the ball going horizontally, that means to the side, and the vertical aspect is, of course, the ball that is in free fall, which we've done those two things separately before. And now we're going to do them in combined problems. So, first of all, let's answer this question. So let's say you had a situation where you had a ball that rolls off a table with a horizontal velocity, and at the same time a ball that is dropped from rest from the same height as the table. So in other words, imagine two balls. And so let's say there's a ball that's rolling, and of course when it leaves the table, it's going to roll like that. And at the exact same time this one starts to fall, there's a second identical ball that's going to fall straight down. Okay. So they're basically falling the same height, but one of them is moving horizontally first. And so the question is this: which of these two balls is going to hit the ground first? The one that rolls off the table, or the one that's dropped from rest from the same height? Okay, so see if you can answer the question. Okay, so I'm going to put a link to a short video clip I want you to watch where you can basically see this demonstration in action. Okay, so take a look at that video. And hopefully what you saw from the video is that the two balls actually hit the ground at the same time. Okay, now the reason for that is because basically the only thing that's different about them is one of them has a horizontal motion and one of them has a vertical motion. So here's one of the key concepts of projectile motion. A projectile is an object that is in free fall that is also moving horizontally. It has both a horizontal and a vertical motion. And the key concept is this: those two motions are completely independent of each other. Okay, aside from the time being the same, they're completely independent of each other. And so that's why the ball that rolls off the table and the ball that's dropped, they hit the ground at the same time, because as far as time goes, the only thing that affects the time is the height. The horizontal motion lives in a completely different world than the vertical motion. Okay, so it's like two separate types of things, and one has nothing to do with the other. Now, to be more specific about the type of each motion, in both situations, the vertical motion, because you're talking about a freefall problem, you have a constant downward acceleration due to gravity. Now, what that means is, for any projectile, you basically have a situation where the vertical velocity is changing. Okay, and the horizontal velocity is not going to change. Now, when I say that, what I mean is that a projectile at any moment in time as it's flying through the air has both an x and a y component of its velocity. Okay, so if you imagine a projectile flying through the air, it has an x component of velocity, vx, and it has a y component of velocity, vy. And if it is in free fall, then it also has acceleration, okay, due to gravity, which has no x component, but which does have a y component. Now, why does it have a y component and not an x component? Well, there's a very simple explanation for that. That's just because the acceleration due to gravity acts straight down. And so typically we associate the x direction with the horizontal, and we associate the y direction with the vertical. And so the acceleration due to gravity, the direction of that is straight up and down, or not up and down, but straight down, which means it acts in the negative y direction. And so that means that this acceleration, remember acceleration just tells you how quickly your velocity is changing at each second. This y component affects the y component of the velocity, but because there's no horizontal acceleration, this x component of velocity does not change. And so for a projectile, you have basically two types of motion at the same time. You have a constant acceleration due to gravity in the y direction, meaning the y component of the velocity changes over time. The x component of the velocity, the horizontal velocity, you have constant velocity, okay, because that velocity is not changing because there is no x component of the acceleration due to gravity. Okay, and that is the key concept of projectile motion. You have these two separate things happening at the same time, the horizontal motion and the vertical motion. One of them is constant velocity, the other is constant acceleration. Okay. And the other way you can think of it is x stuff can only affect other x stuff, and y stuff can only affect other y stuff. Because the acceleration only has a y component, that negative 10 meters per second squared only affects the y part of the object's velocity. Okay, just like this 0 meters per second squared, that's the x component of the acceleration, only affects the x part of the object's velocity. And because it's 0, remember if you have 0 acceleration, you have constant velocity. Okay, so pause there and see if you need to add that to your notes, which you should. Okay, now just to show you this in a simulation form, let me pull up a simulation. And I will link this simulation here in just a second so you can play around with it on your own. I'm going to turn off air resistance, okay, because in the problems we're dealing with, we don't have air resistance. That makes things more complicated. And this is basically a projectile. Okay. It's an object in free fall that's moving in 2 dimensions. You can change the initial speed of the projectile. You can change the angle. You can put it on a cliff or something, make it go higher or lower, like that. But these are all projectiles. Now, by the way, as you're looking at these projectiles, notice that the shape of the trajectory, the shape right here, this is actually a parabola. Okay, and so the for projectiles, you have a parabolic trajectory. Okay, it's just part of a parabola here. Okay, now notice I can actually turn on the acceleration vector and the velocity vector, and I'm going to start with the acceleration vector. And I want you to see how the acceleration of the projectile changes when it's launched. Okay, so this is that yellow arrow that you see right here. And notice that as it goes through the air, the acceleration does not change. Why does it not change? Because it's in free fall, and objects in free fall have a constant, not changing, constant downward acceleration due to gravity. And then, of course, when it hits the ground, of course, that goes away. Okay, and so when I do that again, let's see. Again, we see that yellow arrow representing that constant downward acceleration due to gravity. Now let's take a look at the velocity vector. Okay, so that's this green arrow. Notice that the velocity vector is not constant, it's changing as it flies through the air. Okay, you can see number 1, it changes direction, and number 2, it gets kind of longer over time. And if I want to, I could, make it go higher, I could increase the initial speed, whatever, it doesn't matter. Okay, but that's still the same. Now to help us better understand how the velocity vector changes, I'm going to turn on components so we can see how this changes. I'm going to fire, and now notice we have 2 arrows, one representing the x component and one representing the y component of the velocity. And as the projectile goes through, notice that the y arrow, okay, the y component of the velocity becomes 0 at its highest point, and then the y component now is pointing down because now it's falling down and it's getting bigger. Okay, so the y component is changing over time due to the acceleration from gravity. However, if you look at the x component, the x piece of the velocity never changes. Look at that horizontal arrow. Its length never changes. Okay, because we have constant velocity in the x direction. Okay, so I will link that and so you can play with that on your own. Okay, now concept-wise, that's all there is to solving projectile motion problems. Okay, so now we're going to do some examples, and so you can see how calculations look with this. So first, let's do example 0.5. Look at the image to the right. The football shown is kicked with an initial velocity u. Assume that the x component of u has a magnitude of 25 meters per second. Write in vector component form. Remember, vector component form is with the triangle brackets where you have the x and the y component. Write in vector component form the velocity vector and the acceleration vector of the football at its highest point. Okay, so pause it here and see if you can get that. Okay, and if you've been paying attention, hopefully you figured out that the answer to the question is 25, 0, and 0, -10. Now, where did I get these from? Well, number one, the horizontal motion is constant velocity, which means that if the initial velocity had an x component of 25 meters per second, that x component is never going to change. Even at its highest point, it doesn't matter. So in other words, the football doesn't stop moving at its highest point, it just stops moving up. It's still moving horizontally. Okay? At its highest point, what is 0 is the y component of the velocity. So right here, the velocity would have an x component but a y component of 0. The acceleration, of course, is just the normal acceleration due to gravity that never has an x component, that always has a y component. Okay, so pause there if you need to look at that some more. Alright. And I'll just link a short little video clip in there for you to see the same concept. Okay, so moving on. Here's another question. A bullet is fired from a rifle at the same time that a second bullet is dropped from the same height as a rifle. Which bullet will hit the ground first? Okay, see if you can answer that. Okay, well, hopefully you said that they'll hit the ground at the same time. Of course, that's the same concept that we've been talking about. And so I will include a link to Mythbusters video where you can actually see they basically hit the ground at the same time. Okay, but it's the same question, as long as the rifle is fired horizontally. Now, of course, if you point the rifle towards the ground, then the velocity is going to have a y component, and the one that is dropped is going to have a y component of 0, and so, obviously if you point the gun at the ground, that one's going to hit the ground faster. So this is assuming that the rifle is initially fired horizontally. So let's do calculation problems now. Okay, how do you approach projectile motion problems? Well, remember we have two types of motion at the same time, horizontal motion and vertical motion. The horizontal motion, we have constant velocity. Okay, now remember that the equation for constant velocity is S equals V times T. Okay, this equation only applies for the horizontal motion because we only have constant velocity in the x direction. Okay, that means the only stuff that you should be plugging into this equation is x stuff, x components of stuff. Okay. Now, for constant acceleration, which we have in the y direction, remember we have 4 equations, so I'm not going to write them all down. But we have 4 equations for constant acceleration. And in those 4 equations, you should only be plugging in y stuff. Right? Remember, you can only use those equations if you have constant acceleration. And you do have constant acceleration, but only in the y direction. Okay? Only in the vertical direction. Okay, so make sure when you're doing these problems, you treat all of the x stuff separately from all of the y stuff. All of the vertical stuff is completely separate from the horizontal stuff, and those two things don't interact with each other except through time. Okay, if you have time in one equation, that's going to be the same time in the other type of motion. That's the only thing they have in common. Okay, so we're going to do some examples with problem solving. Okay, so add this to your notes. Okay, so here's how we're going to approach these problems. I'm going to do a couple on my own, and then I'll let you do some as well. Okay, so first, sketch a picture of the situation. Sometimes visualizing the situation can help you understand what's going on. Number 2, if you can, find the x and y components of the initial velocity vector. Okay, because 90% of the time you're going to need the x and y components of the initial velocity vector to do anything in the problem. Now, it says if possible. Sometimes that's the unknown. Sometimes you're asked to find the initial velocity vector, and then you would have to work backwards to do so. But most of the time in a projectile problem, you're given enough information to find ux and uy. Number 3, and this is where people start running into trouble, there's not like always a cookie cutter way to do these problems. What you do is you look at the question you're being asked and you let the question dictate what you do next. If the question is asking you about horizontal motion, then the first place you should be looking is your horizontal motion equation, your constant velocity equation. If the question is about vertical motion, then your first thought should be, hey, constant acceleration equations. Okay, so the question itself, what the question is asking for, is either going to be a question about horizontal motion or about vertical motion. And then you treat those two separate motions from each other completely separate from each other. Okay, the only thing they have in common is time. Sometimes you have to, use one set of equations to find time and then plug that time in to another type of motion equation. Okay, but that's basically how you approach all of these problems. Okay, some of them are going to be pretty easy, some of them are not going to be easy. I will say that generally speaking, you have two types of projectile motion problems that you're most likely going to see. Either you have a projectile being launched horizontally from an elevated position, okay, so kind of like the ball rolling off the table, that type of situation, or you have a projectile being launched into the air at an angle and then landing at the same height. Okay, that covers the vast majority of problems you see in projectile motion. Now, if I want to make things more complicated, then what I would do is I would have a problem where a projectile is being launched into the air, like off a cliff or something, also at an angle. In the free fall unit, we did problems where, cliff problems are challenging because basically you have an up part and a down part and they're not the same. Okay, which means that you have like a quadratic that you have to solve in order to find the total time that's in the air. So those problems can be more challenging. Okay, but these two descriptions basically classify most types of projectile motion problems. Okay, so I'm going to do a few examples so you can get an idea of how to approach these problems. Okay, so example 1. It says a cannon shoots a shell with an initial velocity of 40 meters per second at an angle of 30 degrees above the horizontal. And before I do anything, I'm going to do the first couple steps in this problem. Okay, remember that I'm asked, when I told you how to approach these problems, I said draw a picture. And so basically, the situation in the picture, cannon is shooting a shell with an initial velocity of 40 meters per second at an angle of 30 degrees above the horizontal. So that means the cannon is basically going to be launched at an angle 40 degrees, and it's going to go up and down like this. Okay. So this just gives me like a visualization so I know what's happening. The second step said to find, if possible, the x and y components of the initial velocity vector. Now, watch how I kind of approach this. Let me redraw this picture. So here is u. I'm going to draw u. 40 meters per second. U equals 40 meters per second. That's a given. And I want to find ux and I want to find uy. This is ux. Okay, that is the x component of that vector. This is going to be uy. And then this is 30 degrees. I don't know why I said 40 degrees before. It's 30 degrees. Now, we know how to find components of vectors. We know that, to find uy, that's the opposite side of this triangle. The hypotenuse is the magnitude of the vector. And so I would say sine of 30 degrees is equal to uy over 40. So uy is going to be 40 sine 30 degrees. And that's going to be 20 meters per second. And I can do the same thing for ux. That would be 40 cosine 30 degrees. And I believe that's 34.6 meters per second if I remember correctly. Okay, so we have the initial components of the initial velocity vector. Now, here's what not to do. What some people will do is they'll be like, okay, I just solved for uy, that's 20 meters per second, so that's the maximum height. No, that is completely wrong. This side, don't take this picture I drew too literally. This is not height. Okay, this is, well, number one, this is a velocity vector, so it doesn't make sense that this side would be height. Number two, all we just found was the y part of the initial velocity. In other words, this picture doesn't represent what is actually going to happen in the situation. Remember, what's actually going to happen is the cannon is going to go up and then come back down. Okay, so don't take this uy to have anything at all to do with the height. Okay, first of all. Alright. In any case, now that we've done step 1 and step 2, we look at the question, and we allow the question to dictate what we do next. The question is either going to be about horizontal motion or vertical motion. First, let me write down the components of the initial velocity vector. That would be 34.6, 20, just so I have it for later, so I can erase some of the stuff down here. Okay, so the question is asking me for time, that is my unknown. I have to decide, is that a question about horizontal motion or about vertical motion? Okay, and that is a question about vertical motion. In fact, we've seen that question before because it was in the last unit. How long does it take an object launched up into the air to reach its maximum height? Alright, we've done that before. Alright, that is a vertical motion question. Alright, what is our unknown? Well, it says time, so we're looking for time. Now let's take stock of what we have. We're looking for time. Okay, that is the unknown. If this is a question about vertical motion, we know the vertical motion is constant acceleration, which means I should be thinking about my constant acceleration equations. What do I know about the vertical motion being constant acceleration? Well, I know the acceleration due to gravity is involved, and that is negative 10 meters per second squared. That's always a given in freefall problems. I know that when it reaches its highest point, its maximum height, it stops moving. Or more specifically, it doesn't stop moving, but it stops moving up, which means that the final velocity, or specifically the y component of the final velocity, is going to be 0 meters per second. Okay, what is the initial velocity? Do I have the initial velocity? Yes. Okay, and here's another place people make a mistake. What is the initial velocity here? Well, you might say, oh, the initial velocity is 40, so it should be 40. No, because remember, I'm dealing with vertical motion. Okay, that means the only stuff I should be writing down to do any calculations is y stuff. That means the initial velocity that I really care about is 20 meters per second, because that is the y component of my initial velocity. Okay, so now when I go to plug in, I'm using the equation v equals u plus a times t. I have 0 equals u, again, is not 40, because this is a constant acceleration equation. I only care about the y component of u, because I only have constant acceleration in the y direction. So u is actually uy, that's 20 meters per second. And then I just solve it like a normal problem. Okay, I subtract 20 on both sides, I divide by negative 10, whatever, and I get t equals 2 seconds. Boom. That's it. T equals 2 seconds, and I'm done with that question. Okay, the first part of the question. Pause there if you need to look at it. Okay, so my second question says, determine the horizontal range of the shell. Horizontal range is basically how far does the shell go horizontally. Okay, so I'm going to erase some of this. I'm going to go back to my picture. Remember, what's going to happen is the can shell is going to go up and then it's going to come back down. And so it is going to go up and then down. And so if I want to know the horizontal range, that basically means from here to here, how far did it travel? What is my horizontal displacement? What is Sx? That is what horizontal range is. Okay, anytime you see range mentioned in a question, it's asking for horizontal displacement. Okay, so again, I let the question dictate what type of motion I have. This is obviously a question about horizontal motion. I mean, it has the word horizontal in it. What type of motion do I have horizontally? I have constant velocity. Okay, S equals V times T. Okay, but I only have constant velocity in the x direction, which means I should only be plugging x stuff into this equation. So if I'm looking for Sx, what velocity should I be plugging in? Only the x component of my initial velocity. Because remember, 34.6 meters per second, that was ux. But that velocity never changes, right? Even at its highest point, the y component of the velocity is 0, but the x component is still the 34.6 meters per second because you have constant velocity in the x direction. Okay, so I'm using my constant velocity equation. The v that I care about is only the x part of the velocity, that 34.6, and then the time is the time that's in the air. Now notice that this problem is symmetrical, and we've also talked about this before in the last unit. Because it lands at the same height, if it takes 2 seconds to go up, it's also going to take 2 seconds to go down. So the time we found before was time up. The total time is going to be 2 times 2, which is 4 seconds. All right, as long as the starting height and the ending height are the same, you have a symmetrical problem, and so the time up and the time down are the same. Okay, so 2 seconds up, that means 2 seconds down, that means it's in the air for 4 seconds. So if I plugged in 2 seconds here, I would basically only find half the range. Okay, I don't want the time to maximum height, I want to use the entire time. That's why I'm plugging in 4 seconds here. Okay, so I go to my calculator, I do 34.6 times 4, that's going to be 138.4 meters. And that is the answer to my second question. That is a projectile motion question. Okay, congratulations, you've now seen your very first projectile motion problem. Pause it there if you need to look at that some. Okay, so we're going to do one more, or I'm going to do one more to completion, and then you are going to do one or two more on your own. Okay, now that was the first type of problem, whereby you have a projectile launched at an angle returning to its original height. Now let's take a look at a cliff problem. It says a baseball player throws a ball horizontally off a cliff that's 26 meters tall. The ball lands 32 meters away from the base of the cliff. What is the velocity of the ball? Okay, so step 1, draw a picture. If you took good notes when I literally laid out the steps for you to do for projectile motion problems, then you know that step 1 is draw a picture. Okay, here's the situation. Ball is thrown horizontally off a cliff. The actual trajectory is going to look something like that. Okay, what information are we given? We're given the height of the cliff is 26 meters, and we're told the ball lands 32 meters away from the base of the cliff. So here's the base of the cliff. Here's where it lands. That means we're told that this distance is 32 meters. In other words, if you look at what we're given, we are actually given information about the displacement, both the horizontal and the vertical displacement. We're told, essentially, based on the picture, that Sx, the displacement, the x component of the displacement, how far the baseball goes horizontally, is 32 meters. Sy, on the other hand, is going to be how far the baseball travels in the vertical direction. Because it's falling, Sy should be negative, and that's going to be negative 26 meters. Okay, I got that just from the picture. Yeah. If you're following the steps after you draw a picture, what it says is find, if possible, the initial component, or the x and y components of the initial velocity. But we're not really told anything about the about the initial velocity. It doesn't say anything about how fast the ball was thrown. Actually, that's what we're asked to find. Okay, so let's see. What do we know about the initial velocity? Well, if it was thrown horizontally off a cliff, that tells us something very important. Okay, that tells us that the initial velocity vector, if I draw it, would look like this. What is the y component of the initial velocity? It's going to be 0. How do I know it's 0? Because if it's horizontal, then no part of it is in the y direction. That means ux, I don't know what ux is, but I know that uy is 0. Okay, so from here you let the question dictate what you do next. Now, I know uy is 0. I don't know what ux is, so if they're asking me for the velocity of the ball, they're probably asking me to find ux. That means this is a question about horizontal motion. Okay, so what do I know about horizontal motion? It's constant velocity. I whip out my constant velocity equation, s equals v times t. Remember, I only should have x stuff in this equation because I only have constant velocity in the x direction. And so I know that s is going to be 32. I don't know ux. And I also don't know time. Well, that's not good, so I'm stuck. So I think, okay, if I don't have enough information with my horizontal motion equation, I need to switch back over to vertical motion. Okay, so if I can find the time with my 4 constant acceleration equations, then I can plug that time back in over here. So let's say I want to find the time. I do have uy is 0, and I do have sy is negative 26, and I know the acceleration is going to be negative 10 meters per second squared because the ball is in free fall. So if I want to find the time, I have s, u, t, and a. That means I can pick an equation that has those variables, like this one, and I can plug in. I know that s, or more specifically sy, is negative 26. I know that uy is 0. I don't know time, but I know a is negative 10. Notice again here that for s, I'm only plugging in the y component of the displacement because this is a constant acceleration equation that only applies with constant acceleration. And I only have constant acceleration in the y direction. Okay, that's why there's only y stuff in here. Alright, so I solve that with basic algebra. Negative 26 equals negative 5 times t squared. And I'm going to skip to the end of that. I trust you can do the algebra on that on your own. 26 divided by 5, take the square root, and you get 2.28 seconds. And now I know how long it takes to fall, 26 meters, and I can plug that time back in over here. So now I know that t, this t right here, is actually 2.28 seconds. That means I can just divide to get ux by itself. So ux is going to be 32 divided by 2.28. So the answer to the question is just going to be, forget to divide, 2.28 divide, so that's going to be about 14 meters per second. And that is my answer to this question. Okay, so that is example 2. Pause it there if you need to look at that some more. Okay, so you've now seen one problem of each type for projectile motion. Okay, one problem where you have a projectile launched at an angle returning to the same height, and one problem where it's launched horizontally from an elevated position. Okay, so I'm going to erase this. And I just want to take a look at one more quick example for right now. I want you to pause it here and try to do example 3 on your own. And now let's see how you did. Okay, my first step is to kind of sketch out the situation. I know that it's launched at 35 degrees above the horizontal. Cannon is going to go up, down, or the cannonball is going to go up and down like that. Second step, find, if possible, the components of the initial velocity vector, uy and ux. Ux is going to be 120 cosine 35 degrees. Okay, that's going to be 98.3 meters per second. And then Uy is going to be 120 sine 35 degrees. And if you didn't do this, then you're not following the steps I explicitly gave you to solving projectile motion problems. I even numbered them for you a couple slides back in the notes. Okay, this is just step number 2. Okay, find if possible the components of the initial velocity vector. Then you let the question dictate what you do next. If the question about height, that's a question about vertical motion. I know that because, height is up and down, and, that's obviously vertical motion. So my first thought should be, hey, I'm solving with constant acceleration equations. I'm looking for Sy. I have Uy is 68.8. I know there's acceleration due to gravity, and I know at maximum height, the y component of the velocity is 0 meters per second. So I choose the equation that has s, u, a, and v in them. That's v squared equals u squared plus 2as. And I plug in and I solve. 0 equals 68.8 squared plus 2 times negative 10 times s. And I will just write down the final answer. That is 236.7 meters. That's Sy. Okay, and so hopefully that's what you got, or at least at this point, hopefully you know what you did incorrectly. Remember to keep all of the x stuff completely separate from all of the y stuff. Okay, so pause there if you need to look at that some more. Okay, so just in case you want to do one more example on your own, there's lots of examples on your practice worksheet for you to work on, but if you want to do example 4 on your own, I will write down the answers so you can check yourself. Okay, so pause it here and try to do example 4 on your own. Okay, and so you can check your answers here for example 4. Okay, so hopefully you got this correct. If not, let me know and I will do my best to help you out. This is the end of the projectile motion unit. Please make sure you do all of your practice problems and ask for help if you need help. Okay, as always, let me know if you have any questions, and I'll see you guys in the next video.